For the beam loaded as shown by area moment method, determine the slope and deflection at points B and C. EI is constant. Here is the given figure. So we select D as our moment center. We don't need to compute for the reactions. So first, for 20 times 8, it's 160 over EI. Then 30 times 5, so additional triangular moment diagram. By the way, this is 60 over EI. 20 times 3, 60 over EI. Then this is 30 times 5, 150 over EI. Since 160 plus 150 is 310 negative, so the moment due to the reaction at D would be 310 over EI. So in other words, 310 divided by 10, so the reaction here is 31 kilonewtons, but not important. So the coordinate here, the moment here would be 2 over 10, 0.2 of 310. That would be 62 over EI, or 31 times 2. 31 times 5, or 310. This is 5 over 10, so 0.5 of 310, 155 over EI. So this is the complete moment diagram by parts. Let's anticipate the elastic curve. This is the tangent at A, therefore this is the deviation of D relative to the tangent at A, which is expected positive. Obviously positive because D is above the reference tangent, and of course the elastic curve will look like that. So let's evaluate this. This is simply the moment of areas with respect to D. So call that theta A, and because this is correct, though this is positive, theta A is negative because the tangent is sloping down to the right, or the tangent line is from the positive x-axis to the tangent line, it is clockwise. Clockwise is negative. So EI deviation of D relative to the tangent at A is 0.5 of 10 times 310 over EI. The centroid of the triangle is here, and its distance from D is 1/3 of 10, so that's why we have 10/3. Then minus this area, 0.5 of 8 times 160 over EI, then this distance is 8/3. So 0.5 of 8 times 160 over EI times 8/3. Then minus this area, 0.5 of 5 times 150 times 5/3. 0.5 of 5 times 150 times 5/3. Computing deviation of D relative to the tangent at A, using your calculator there, it is equal to 2835 over EI. Therefore, we can now compute theta A. Remember, tangent of theta A is equal to theta A itself. It is negative of 2835 over EI divided by 10 meters. So theta A is negative of 2835 over EI over 10. So theta A is negative 283.5 over EI. Then we draw tangent to B, and let's evaluate this angle. This is theta AB, the angle between A and B. If it is correct, as in the figure, the rotation is counterclockwise from A, so it is positive, and it is simply the area between A and B in the moment diagram by parts. So that's the horizontal through B. So this is theta AB. From this tangent at A to the horizontal, that's theta A also. And therefore, from the tangent at B to the horizontal line, that's theta B. If this figure is correct, then theta B is also negative. Negative of absolute value of theta A minus absolute value of theta AB, as long as the sign of theta B is negative. So let's evaluate theta AB. AI theta AB is the area between A and B. So 0.5 of 2 times 62, that's 62 over EI. Theta AB is 62 over EI. Then based on the figure, theta B, because 62 over EI is lesser in magnitude than theta A, so the figure is correct. So theta B is really negative. So theta B is negative of absolute value of theta A minus absolute value of theta AB. So this is negative of absolute value of theta A, this is theta A, minus theta AB. So therefore theta B is equal to negative 2 to 1.5 over EI. Just like theta B when we solve this in example 100D by double integration method. Next, for deflection at B, let's solve for deviation of B relative to the tangent at A first. This distance of point B on the elastic curve to the reference tangent is the deviation of point B relative to the tangent at A. And it is the moment of area between A and B with respect to B. Then the entire distance from the horizontal axis of the beam to the point on the reference tangent, because the distance from A is 2 meters, so that's 2 times theta A. And therefore, this deviation is the deflection. This vertical distance is the deflection at B, which is again negative. So let's evaluate deviation of B relative to A. AI division of B relative to A is 0.5 of 2 times 62 times 1/3 of 2, 2/3. So therefore, it is equal to 124 over 3 EI. Positive because B is above the reference tangent at A. So therefore, delta B is negative of absolute value of 2 times theta A minus absolute value of deviation of B relative to the tangent at A, which we have just computed, 124 over 3 EI. So this is negative of 2 times theta A on the figure minus the absolute value of deviation of B relative tangent at A. So you just look at the figure. So delta B is negative 525.667, just like in problem 100D. Next is, let's draw the tangent at C. Let's evaluate AI theta AC. This is the area between A and C. So 0.5 of 5 times 155 minus 0.5 of 3 times 60. So just these two areas. So the theta AC is equal to positive 297.5 because the tangent from A to tangent at C rotate counterclockwise. Counterclockwise rotation is positive. Because theta AC is greater in magnitude 297.5 than theta A, it means that the angle between the tangent at A to the tangent at C is greater than theta A. So it exceeds the horizontal. So this is the horizontal line because the tangent at A to that horizontal line is theta A. Theta AC is greater, so it is above that horizontal line. So that's theta AC. This is theta A. Therefore, the tangent at C is above the positive x-axis, so it is positive. That's theta C. And from the figure, it is positive of absolute value of theta AC minus absolute value of theta A. So theta C is positive of absolute value of theta AC, which is 297.5 over EI, minus absolute value of theta A, which is negative 283.5 over EI. So don't mind the sign, because that's absolute value. So theta C is equal to 14 over EI. So that's the same as in double integration. Then this is deviation of C relative to the tangent at A, which is positive because C on the elastic curve is above the reference tangent. The distance from the axis on the beam, horizontal axis of the beam, to the point on the reference tangent is 5 times theta A, because this is 5 meters. So that's 5 times theta A. And this is the deflection at C. And it is negative. So deflection at C is negative of absolute value of 5 times theta A minus absolute value of deviation of C relative to the tangent at A. So let's evaluate deviation of C relative to the tangent at A. It is the moment of areas between A and C with respect to C. So EI deviation of C relative tangent at A is, we copy these areas, then moment arm 5/3 minus this area 0.5 of 3 times 60, moment arm is 1. So deviation of C relative to the tangent at A is equal to 3335 over 6 EI. Finally, delta C is negative of absolute value of 5 times theta A minus 3335 over 6 EI. Expressing the answer in decimal form, delta C is equal to negative 861.667 over EI. So that's it.